Hi students, in the last video we talked about vertical asymptotes, which were vertical lines that the graph approached and started to look like as it got close to the x value, which the vertical line went through. A horizontal asymptote is a similar idea. When you get toward a horizontal asymptote, the graph might be coming up to it, but then when it gets there, it's going to start to look like that horizontal line. So let's first look at some examples and give a definition. The definition is the line y equals b is a horizontal asymptote of the function f if f of x gets close to b as x gets close to infinity or as x gets close to negative infinity. So it means eventually, so if here are your axes and this is the line y equals b, that means even though things might happen in between, eventually as x gets really, really big, the graph starts to look like this line. So y equals b again is not part of the graph of f, but the graph of f starts to look like it as the x values get bigger. So here's an example, again, one you've seen before. This is the graph of 1 over x. So as the x values get really, really big, the graph starts to look like the horizontal line y equals 0. But we know that this function, 1 over x, can never actually equal 0, so that makes it a horizontal asymptote. So the horizontal asymptote is at y equals 0. And again, that's just because the graph looks like this. And here's the line, y equals 0. So let's look at another example, 2x over x squared plus 1. So we have 2x in the numerator and x squared minus 1 in the denominator. So here, there's a lot going on in the middle of the graph, you'll notice. But as the x values get large, it starts to go toward the line y equals 0. Similarly, as the x values get closer and closer to negative infinity, the y values of the graph get closer and closer to 0. This sort of makes sense because as the x values of this function are getting really, really big, say you plug in 1 million. So we have 2 million in the top. We have a million squared minus 1 in the denominator. Well, this minus 1 doesn't really matter. So this looks kind of like 1 million over 1 million squared. So we could cancel out the million on top, so it's like 1 over a million. So we're dividing by a really big number, so it should be pretty close to 0. So basically what I just did is I said, as x values get really, really large, this thing is going closer and closer to 0. That's what we're saying up here. As x is getting really, really large, f of x is getting closer to some value. In this case, that value b happens to be 0. It starts to look like 0. So one more example, 2x minus 1 over x. Let's use the same logic again. So say we plug in a million into this one. So we'd have 2 times a million minus 1 over a million. So this looks like 2, this minus 1 doesn't really matter all that much, right? So it kind of looks like 2 times a million divided by a million. So what's that going to be? It's going to be pretty darn close to 2, but I'll show you in the calculator that that's true. So there's 2 times a million minus 1. Then we divide that by a million. Oops, I did too few zeros, but that's okay. I did the same number of zeros in this as this, so I actually plugged in 100,000, but that's quite all right. So 2 times 100,000 minus 1 divided by 100,000 is pretty darn close to 2. I guarantee if you did 2 times a million minus 1 divided by a million, this is going to be pretty darn close to 2. So as the x values go toward infinity, the y values are getting closer to 2. So this is going to tell us that the horizontal asymptote should be at 2. And we can check that in the graph. So let's do it. In the numerator, we have 2x minus 1. In the denominator, we have x. And there's our graph. As the x values get really, really large, the y values are getting closer and closer to 2. We can see that in the table. So let's start at 0, our table step. Let's go by 10. Look at the table. As our x values are getting bigger and bigger and bigger, the y values are getting closer and closer to 2. They never get bigger than 2. I can get as big as I want with x, and the y values are just getting close to 2, but no bigger. So this is another way to see that 2 is a horizontal asymptote. A horizontal asymptote is a y value that the graph gets closer and closer to, but never actually reaches. So let's come up with some rules for determining horizontal asymptotes. In these examples, well, you'll notice that this one had a horizontal asymptote at 0. So did this one. And this one had a horizontal asymptote at something besides 0. It had a horizontal asymptote at 2. If we compare these two functions, notice that the degree of the polynomial on top was smaller than the degree of the polynomial on bottom, which means the bottom polynomial was getting very, very large in a much faster way than the top one. So that dictates our rules. It means we're dividing by bigger and bigger numbers if the degree on bottom is bigger. So this type of rational function will have a horizontal asymptote at 0. So here's the rule, and you can just follow the rule if what I said makes no sense to you. The graph of f will either have one or no horizontal asymptotes. The horizontal asymptotes are determined by comparing the degrees of the polynomial on top, so this is the numerator, and the polynomial on bottom, the denominator. So if the degree of the numerator is smaller than the degree of the denominator, then the graph of f has the line y equals 0 as a horizontal asymptote. That was the case in our first two examples. The degree on top was 0, the degree on bottom was 1, and we had a horizontal asymptote at 0 because we were dividing by much larger numbers than the numbers that we had on top. Here, the degree of the top was 1, the degree of the bottom was 2, and so the numbers we were dividing by were much, much bigger than the numbers in the numerator, which means the horizontal asymptote was 0. So if the degree on bottom is bigger, you have a horizontal asymptote at 0. You can use that as a mantra. Repeat it to yourself. Degree on bottom bigger, horizontal asymptote at 0. If the degree on top is equal to the degree on the bottom, then we have another special case. We have the line a sub n over b sub m, which is the ratio of the leading coefficients, is the horizontal asymptote. So that was the case in our last example. Here, the degree on top was 1, the degree on bottom was also 1, and a sub n, the leading coefficient of the top, was 2, b sub m, the leading coefficient on the bottom, was 1, so we had a horizontal asymptote at 2 over 1, which is a sub n over a sub m. That's 2. So the reason that this is because the top and bottom are growing at the same rate. The x's sort of cancel, just like these 1 millions sort of canceled. So when x is really, really large, all that matters is these leading coefficients, because this minus 1's not going to cancel, or it's not going to matter. So we'd have something that looks like 2x over 1x. We could cancel the x's. That will look just like 2. So the next mantra, if degree on top is same as degree on bottom, the horizontal asymptote is the ratio of the leading coefficients. Ratio of leading coefficients. Now in the last case, if the degree on top is bigger than the degree on bottom, that means that there are no horizontal asymptotes. Now, why might that be? Well, here's an example of one where that's the case. Let's look at x cubed plus 2x, or plus 2 over x. Well, when I'm plugging in really, really large values for x here, like 1,000,000, this is going to look like 1,000,000 cubed plus 2 divided by 1,000,000. The top is much, much bigger than the bottom, so this function's just going to keep growing as x gets large, so as x goes to infinity. You can check that in the graph. So let's look at x cubed plus 1 over, or plus 2 over x. And you'll notice that as x gets big, this function is still growing. So we could zoom way out, minus 100 to 100. As x is going to infinity, that function keeps on growing. So it will have no horizontal asymptotes if the degree on top is bigger than the degree on the bottom. So to finish off this video, let's do two examples where we find both the vertical and the horizontal asymptotes of a function. So to find the vertical, we first simplify, but this is already factored, this is already factored, we can't cancel anything out, so we've already simplified essentially. Then the vertical asymptotes are the zeros of the denominator. So if we were to try to find this, we'd be looking for values of x such that x squared plus 1 equals 0, or x squared equals negative 1. So there are none, no such values. So this has no vertical asymptotes because the denominator has no zeros. Then the horizontal asymptotes are dictated by the degree. So since the degree on top is 2 and the degree on bottom is 2, we have that the degree on top equals the degree on bottom. In this case, we take the leading coefficient of the top and divide it by the leading coefficient on the bottom. So the asymptote is y equals 2 over 1 equal to 2. Now we can check our work by looking at the graph. 2x squared divided by x squared plus 1. Graph it, normal zoom. So there's no vertical asymptote, there's no vertical line anywhere here that the graph starts to look like. Here you go. And there's no zeros of the denominator, so the domain is all real numbers. And we have a horizontal asymptote at y equals 2. The graph starts to get close to y equals 2 as the x values get bigger and bigger in the positive direction and the negative direction, but it never crosses. So one final example, 3 over x minus 2. So the vertical asymptotes are the zeros of the denominator, so it should be at x equals 2. And the horizontal, so since the degree on the top is 0 and the degree on the bottom is 1, the degree on the bottom is smaller. So since the degree of the denominator is bigger, I might have said smaller before, the degree of the denominator is bigger. Since the degree of the denominator is bigger, the horizontal asymptote is at y equals 0. And that's coming from this rule. If the degree on top is smaller than the degree on bottom, then the graph of f has y equals 0 as a horizontal asymptote. And you can see that as you plug in a large number for x, the denominator is getting really big, so the whole function is getting closer and closer to 0. Okay, so I hope